In this video, I want to show you how to use spin of two dice to demonstrate normal distribution. Well, obviously the curve you are going to get is not exactly going to be normally distributed, but it will give you some idea how we started thinking about the normal distribution curve. Why do we need it? Because we want to problem solve in easier way, and some of the graphs are so complicated and quite different if you are using it for one school to another or in different places. So we want to use something which is standardized, a kind of model for our probability findings. So why do we need normal distribution? It's to work out the probability of certain thing can happen. As you can see, the distribution is building up. What is the distribution for? These are the summation of counts for two dice roll. So if you are rolling once, you get the topmost number as 6 and 2. That will add up to 8. So that gives you some idea actually how it's going to work. Look at the tendency. The graph has most of the distributions, the top ranking distributions, right in the middle, and we know by now 70% of the main stuff is centered around 70% of the probability. Within 3 standard deviation, your teacher is going to explain it to you what standard deviation stands for. The most of your data will lie. I am trying to show you some idea actually how a continuous process can be simulated from a very discrete data. So I think rest of the video is going to be pretty self-explained. I'm trying to use the insight to demonstrate how a proper normal curve happens. At this stage, probably you'll find it a little bit challenging to understand it, but the thing is that 523.24 is the mean value of the distribution. I can't even remember. These are the distributions of trouts in Lake Taupo, and as you can see, I am doing taking lots of sample because without that you cannot reach the precision level of your calculation. And if you look at this particular developing graph, this is what will demonstrate a normally distributed graph. Possibly this is the closest possible thing we can simulate to a normal distribution, which is a symmetrical, very sort of refined and elegant kind of distribution. We sometimes call it a bell-shaped curve. And why do we call it a bell-shaped curve? Because if you are thinking about a dingle bell, and if you cut it along the cross section, it will look like a kind of semi pear-shaped curve. So once again, I'm demonstrating the same thing. As looks like a pile of dirt building up, but uniformly building up, always trying to follow the center of the data, which is 523.24.